Suppose a cameraman stands on flat ground 600 feet away from a rocket that is set to take off. Upon ignition, the rocket rises at a rate of 200 feet per second. 4 seconds after ignition, at what rate is the distance between the rocket and the cameraman increasing? For these problems, and in similar problems, when we have a type of picture that we could visualize, it often helps. So let's start off by seeing what is actually happening here. We have our cameraman. He's standing on flat ground, and here is our rocket over here. The cameraman stays a distance of 600 feet away from the rocket. The rocket starts to take off, rising at a rate of 200 feet per second. So as we start to realize what's happening in our picture, the rocket is here, then the rocket continues to go up. 4 seconds after ignition, at what rate is the distance between the rocket and the cameraman increasing? Well, again, go back to our picture and realize how it continues to change. The initial distance between the cameraman and the rocket is just the ground level. Then as the rocket begins to rise, that is the distance between them. And then as it continues to rise, we continue to get a longer and longer line. And now as we draw our picture, we start to see a very common situation. We start to see a basis of a right triangle situation. And when we look at our right triangle, the bottom side, the 600 feet, remains constant throughout the problem. But as the rocket continues to rise on the far right side, that side of the triangle increases. And then the hypotenuse, which represents the distance between them, also increases. Our question is, at what rate is the distance between the rocket and cameraman increasing? We use a variable to represent this side of the triangle since it continues to change. And we also realize that the far right side continues to change, so we use a variable for that side as well. We recognize the 200 feet per second is the rate at which the side of the triangle increases. So we should identify that as the derivative. And since we label that side y, that derivative will be marked dy dt. And back to the question, 4 seconds after ignition, at what rate is the distance between the rocket and the cameraman increasing? D itself represents that actual distance. The question is, at what rate does that change? At what rate is that distance increasing? So the whole question is focusing on what is the derivative of capital D with respect to t. The second piece, many of our problems have a moment. D and y continue to change. We want to find this value d dt 4 seconds after ignition. So we know some information about y and dy dt. We want some information about d and d dt. What is the relationship that connects the original variables? We're focusing on the sides of a right triangle, so we're thinking of the Pythagorean theorem. Our a squared plus b squared equals c squared. In this particular problem, the 600 never changes, so that side remains constant. The y continues to change, so we still need our variable. And then d continues to change, so we still need our variable. We're using the Pythagorean theorem, just making it specific for our exact situation. But the question is actually about the derivative. So we will now take the derivative of this relationship with respect to t, with respect to time. Taking this derivative, taking the derivative of both sides, 600 squared is just a constant, so the derivative is 0. The derivative of y squared, 2y, but that gets marked dy dt, equals the derivative of d squared, 2d dd dt. We want d dt, so that means we need values for y, dy dt, and d. It seems like we only have information for dy dt, but we also have our moment. D and y continue to change, but we want this information exactly 4 seconds after ignition. Well, if we look at that situation, 4 seconds after ignition, if the rocket is rising at 200 feet per second, that will tell us that the rocket has gone a total distance, has risen a total of 800 feet. Once we have that piece of information, we can go back to our original Pythagorean theorem and realize in that particular moment, the base is 600, the far right side is 800. We could use the Pythagorean theorem to solve and figure out that D is going to be 1000. Now we have all of our information to plug in and we can solve. 0 is just 0, so we could pretty much ignore that. So we have 2 times 800 times dy dt, which is 200, equals 2 times d, which is 1000, times dd dt. We solve for dd dt, and we get an answer of 160 feet per second. Now, there is a second part to this problem. Very similar, so I'm going to just start with another fresh picture and realize that we're in a very similar situation. Once again, we have our cameraman, we have our rocket. They are a distance of 600 feet apart. The rocket rises at its 200 feet per second. But this time, 3 seconds after ignition, at what rate must the cameraman rotate his camera to keep the rocket in focus? We're not looking at the distance between the cameraman and the rocket. We're focusing on the angle that he makes. Once again, we still see the picture. The rocket continues to go up, so we still get this nice right triangle situation again. But again, instead of focusing on the 3 sides, we're keeping in mind how the cameraman changes his angle. So this time, instead of focusing on the hypotenuse, the D, we're actually looking at the angle that he actually makes. And again, we're not asking the question about what is the angle. We're looking at what rate he must rotate his camera, at what rate he changes his angle. So this time, we're looking for d theta dt 3 seconds after ignition. Well, what other information do we have? We still have the same information from earlier. We still know about how the rocket actually increases. We still have to recognize that that is a changing side of the triangle, so it requires a variable. And the rate at which the rocket rises is the rate at which that side of the triangle increases. So we once again have that same information, that dy dt equals 200. So we know information about side y and its derivative. Not interested in the hypotenuse this time. I'm interested in the angle. So we have a right triangle. We're focusing on the angle. What is the connection between angle theta and the side y? Well, we need a trig function. We could use a lot of different trig functions, but the easiest one we could use is to also keep in mind that we also know the base of this triangle. So looking at angle theta, we know some information about the opposite side. We know some information about the adjacent side. We will use tangent of theta is equal to y over 600. That is our relationship amongst the original variables. But once again, the question is actually about the derivative. We want to know information about d theta dt. So once again, we will take this original equation, original relationship, and take the derivative with respect to t, with respect to time. On the left side, the derivative of tan theta is secant squared theta, and we mark the theta d theta dt. On the right side, a lot of people are tempted to use quotient rule, but keep in mind, y divided by 600 is the same thing as 1 over 600 times y. So instead of using quotient rule, we could just use the idea 1 over 600 times y has a derivative 1 over 600 times dy dt. So a different relationship, but now that we have the derivative, we're still in a similar position that we were in with part A. We want information about d theta dt, we know information about dy dt, but we need to know what theta is in order to solve for that. Now, once again, theta continues to change, but we have to come back and focus on our moment. The moment we want this information is 3 seconds after ignition. So once again, let's use that to fill in a couple of our unknowns. Similar to the first one, if we know the rocket rises at 200 feet per second, And if the rocket has been traveling for 3 seconds, we know at that moment, y has a value of 600 feet. From here, we can use that to help us find theta at that moment, similar to the first one, how we use that information to find d. We could either come back to our original relationship and realize when y is 600, we get tangent of theta equals 600 over 600, which just simplifies to 1, and realize what is that angle? That is the angle pi over 4. Remember, we're dealing with derivatives, so we can't use 45 degrees here. We have to use radians. In this problem, there happens to be a second way to figure out this angle. If we just remember some geometry facts, the base of our triangle is 600. In this moment, the opposite side of the triangle is also 600. So we have an isosceles right triangle. So in this moment, you have a right angle here. These two angles must be the same. Therefore, they both must be 45 degrees or pi over 4 radians. We finally have all of our information. We're ready to plug in and solve for d theta dt. Secant squared of pi over 4 times d theta dt equals 1 over 600 times 200. The right side just becomes 1/3. A little bit of work. We figure out secant squared of pi over 4 is 2. So we finish solving d theta dt equals 1/3 divided by 2, 1/6 radians per second.